Good evening and welcome back to Vegas October 1 Sounds. Tonight I'm going to be covering a little bit of a technical aspect about gunshot acoustics. And the subject matter for tonight is what does changing the recording location relative to the barrel of the gun do to this signal? That is, if you're not directly in the path of the bullet or directly in line with the barrel of the gun, how does that affect the sound? To date, I've been using relatively simple models about the formation of the sound from both the muzzle of the barrel and the sounds generated by the supersonic projectile from that rifle. And those are models. They're simple. They're pretty good in predicting what should or should not be heard. But there are variations when you move the path of the bullet or the angle at which the gun barrel is pointed relative to the recording device. So, what I'm going to do is present the theory that this fellow has developed in a very simple way. I'm going to present this theory without a lot of math. If you understand how to draw on a computer screen, and if you can bring up Audacity or something like that and read a waveform, that's pretty much all you need for this evening's broadcast. So anyway, I refer to this fellow a lot. He's an electrical engineer and computer scientist up at Montana State University. His name is Robert Maher, and he does a lot of research into the forensic of gunshot acoustics. And many times I'll refer back to his research to give me familiarity regarding the theory and practice of looking at these audio signals and interpreting what they mean. So if you wish to see more from him, you can go to this website up at Montana, montana.edu/Maher, MAHER/research.html. And in there he has, bunches of papers, bunches of research, and it covers quite a few topics on the nature of gunshot acoustics and the interpretation and verification and presentation in court and etc. of these acoustic interpretations, or the forensics of audio analysis. Anyway, let's focus it down to tonight. And tonight I'm going to be talking about what happens when you change the angle between the recording and the gun. But before we get into these waveforms, let's go draw a picture of what's happening here. Alright. So Mr. Maher has created a setup where he has a gun. Well, actually, let's draw the side perspective. So here's the ground, and then Mr. Maher mounts a gun up here somewhere a few feet above the ground, and then he puts microphones at various locations downrange. So if the bullet was fired, it'd come out this way, and then he puts microphones, sometimes up below, sometimes above, sometimes below. If you look at this from an overhead perspective, then what you'll see is a gun, and then you'll see microphones placed at various locations. Okay. So if the bullet is to come out the barrel of the gun like this, we call this 0 angles, 0 degree angle. That's on axis, and then each angle subsequently would be increasing until you reach 90 degrees, and then it would increase again until you reach directly behind the gun, which is 180 degrees. So when he refers to that angle, that's what we're talking about. So how does the signal look at each one of these little green places for the same exact gun, the same exact bullet, the same exact firing. Now, of course, he has to do multiple shots, and there's a small amount of variation with each one. To do this stuff, he has a really high-grade microphone. He has a really high, which can handle the massive amounts of pressure, because he records these things on the order of 30 feet away from the gun, which at that distance, if you're somewhere over in here, is pretty darn loud. So the dynamic range of these microphones is good, and he also samples the signal to convert to a digital recording at typically 100,000 hertz or 128,000 hertz, which is 2 to 3 times greater than what your typical high quality recording occurs in a cell phone or a smartphone or whatever you want to call it. So he's able to capture far more than what we can capture or have captured on the smartphones that night in Vegas. So he gets a much cleaner picture of the signal. Now, if you remember, we're going to be talking about two things. One is a muzzle blast, which is the sound that the gases which escape out the end of the barrel make. So the bullet goes off, the round fires inside there, and then all these gases go push the bullet out, and then it pops out and makes this sound, which theoretically propagates in a fairly even sphere around the gun. On the other hand, the bullet going along this way at supersonic speeds, the second thing we talk about is a supersonic crack. That's the sound of the bullet, not an actual definition of what it is. And it's the sound we hear when the conic shock wave generated by the bullet all along here comes across our recording the area. So we're going to be talking about two things: the muzzle blast and the supersonic crack that we hear. All right. So if we go back over to this, and let's go ahead and erase all that crap. Then, this is a waveform plot, and on the left-hand side you can see that we have that angle I was talking about. He calls it the azimuth angle. So 0 degrees represents being aligned directly in front of the barrel. 90 degrees down here somewhere represents being, either left or right. It doesn't matter because the sounds are symmetrical about the path of the bullet. And then, further down at 180, that's behind the gun. The little signal we hear is the shock wave from the bullet. And let me just so this is the shock wave right here, which is created by the bullet, and then this is the muzzle wave over here, this larger thing. Each of these lines is 1 millisecond or 1,000th of a second. So in this case, first off we have to observe something. If we're directly downstream from the bullet, then the distance between the arrival of the shock wave from the bullet to the time of the arrival of the muzzle blast is what I've been referring to as lag, but it's simply the difference of the time of arrival. And in this case we are, let's call that 1/3 of a millisecond, that a full millisecond, and that 2/3. So we're about 2 milliseconds apart, or a lag of 2 milliseconds. So that's a very, very short time. And this time is predicated upon, as I've explained many, many times, the downrange distance, how far you're away from the shooter, and the cross range, which actually is a function of this azimuth. For him, he's recording only a few tens of feet away, and at the speed of the bullet, which is 2 or 3 times the speed of sound, the lag isn't going to be very large. The further away you get from the gun, the bigger this lag would become at a specific angle. So at this angle, this lag is almost strictly determined by the distance from the shooter. In this case particularly because he's on the ground and he's firing horizontal to the plane of the ground. But as the angle increases, things happen. But just to characterize this for a moment, you can see that the shock wave here is what they call N wave, because it looks like an N. I've colored it now here in red, and it's very, very short. The width of that thing is less than a millisecond. In fact, it's, on the order of, in actuality, it probably occurs when it's generated by the bullet itself in the range of less than 100 microseconds, but because the air can't respond that quickly, it expands out to somewhere on the order of 200 to 500 microseconds, or half a millisecond. As you can see here, it's not near half a millisecond, but close. And to characterize the muzzle blast, you can see it is much, much wider. It's two to three times, maybe even more if you consider some of the tail parts over here, wider than the supersonic crack. And I'll show you what those things look like when I get into a frequency display of them. But tonight what I want to talk about is what happens as either the barrel of the gun sweeps away from the recording, a fixed stationary recording, or a recording location is pushed off to the side. And he's going to express this as a function of the angle between the two, regardless of how far away you are. So this is well, let's see, if we go back over to his web page, there's a picture in here. So, oh yeah, there we are. In this picture, if we blow it up a little bit, we can see he's got this array of microphones, which is it's kind of in a semicircle around him, so that he can measure simultaneously for one shot that he fires all things at once, for all the angles at once. So, there he is out on the plains of Montana. He, for some reason, does a lot of this work when there's ice on the ground, because it represents a hard surface. I don't know why, but anyway, so there he is. So back over to this asthma thing. So, as you can see in these cases, the signal varies, and it varies pretty substantially. Here's the strongest signal will be direct on, both for the shock wave. If you're recording directly downstream along the path of the bullet with very little distance between you and the bullet, then you're going to receive the strongest signal for both the shock wave and for the muzzle blast. Now in this case, since we are close, the muzzle blast is much stronger, i.e. larger amplitude than the shock wave. The further away you are, the muzzle blast dies down. It becomes smaller and smaller and smaller. But if you stay on path with the bullet, then the supersonic shock wave stays the same amplitude. So relatively speaking, it increases in size relative to the muzzle blast, provided you're at 0 degrees downstream larger. Okay, but anyway, let's look at here what he shows. As the angle between the recording device and the gun increases, then the shock wave gets closer and closer to 0 lag. And at some point, in this case somewhere between 33 and 49 degrees, there is no more supersonic shock wave. Or actually there is, but it occurs identically at the same time as the muzzle blast, right on top of each other. So there would be 0 lag, which is an interesting phenomena that I haven't really talked about much. And it's due to the nature of the formation of the shock wave and the speed of the bullet. There is an angle at which both the muzzle blast and the shock wave arrive at identical times. And for this case, which I said again, this is for a .308 rifle, so it's not going Mach 3, it's probably less than Mach 2, but not much more when when he's recording up close. Now for Vegas, down there at the venue, a .308 rifle is most definitely, well, you can look up the ballistic charts for a .308, round fired typically. For a .223 round, because it's a lighter round, it slows down much quicker than a .308. And even though the 308 is fired at a lower velocity, it maintains that velocity. So for a 223 round fired from the Mandalay Bay and reaching out as far as the venue, it's down in below the Mach 2 range there. And probably not too far out there on the east side of the venue in the dirt parking lots or near the church, it has probably gone transonic or subsonic in speed. But again, that varies upon the bullet load and everything. But we're just talking the typical Remington 55 grain, muzzle. Load. Now, but back again once here, we notice that as you increase this angle between the recording and the gun, the signal decreases in amplitude until when you are behind the gun, both the muzzle blast and the supersonic crack have essentially disappeared. Now, if you were to magnify this or amplify it a lot, there's still signal there, but making anything out of it is problematic. And so you can see that the bigger the angle, the less similar the wave is to the one that's on axis or at 0 degrees. In fact, Mr. Maher goes on to assert in a paper that these signals are so different that they look like different guns. If you were just to be presented the signal with no knowledge otherwise of it, which is often the case in when you're doing the forensic analysis, it could look like a totally complete gun, different gun. And that's the trouble here. So as you see, increase the angle. First off, as you increase the angle, the amplitude reduces, not in a linear fashion either. And the same thing is true for the shock wave from the bullet, but in this case it's so close it doesn't make a lot of difference. But the important thing to note here is that as you increase the angle, the distance between the arrival of the shock wave and the arrival of the muzzle blast diminishes. Okay, now the shock wave always arrives first and can't go to the right of the muzzle blast, i.e. arrive after it, as long as it's supersonic. So the shock wave will always arrive first. But as you increase this azimuth angle, the shock wave gets closer and closer to the muzzle blast. Now, in real terms, what does that mean? That means if I'm firing out of the window from room 135 towards the venue, then things to my right at large angles will have less lag. That is, the shock wave and the muzzle blast will arrive. So if you're out at the Oasis Apartments at 45 degrees to where the bullet was fired, then you're going to have small lag. If, however, you're at, let's say, the East Side VIPs, where you're almost dead on, you're going to have large lag because the angle is small. And I hope people can visualize that. Now, this is for a 308. Let's go down and see what he says about other guns. Well, for a Glock pistol, which has no supersonic bullet, you only get the muzzle blast. And it too suffers from the same phenomena. In fact, it's much more degraded on the angle. You can see this is a fairly typical end wave where it goes up quickly, comes down at a fixed angle, and goes back up to 0 pressure. But once you reach that 49 degree mark, things start to run amok, and the signal just continues to degrade until it's unrecognizable as that thing at 0 degrees. Let's look. This is a Ruger SP-101 357 caliber revolver. So here again we see the muzzle blast. There's no shock wave, supersonic shock wave, because there's no supersonic bullet. And you can see it's pretty clean up there. And the further down you get, it starts to have a lot of different little peaks to it, until here at 98 degrees, the secondary peak over here is actually larger than the primary peak. So, people say that, when they hear a sound, particularly the muzzle blast, sometimes, the second echo that they hear, or the first echo they hear, is louder than the primary signal coming from the gun, and that's maybe typical if you're at large angles. It's a different phenomenon if the angle is small. So anyway, once again, this one too suffers as you get down. If you're directly behind the gun, then the muzzle blast, becomes fairly non-existent. So the old model of a spherical, evenly spaced, evenly distributed propagating muzzle blast is technically not true, but for locations in front of the gun, which is almost always what we're talking about in Vegas situation, it is true, or at least it's a good model. So this is a 12 gauge shotgun, and here you can see that it's much noisier than the revolvers were, and even going as little as 33 degrees you start to wonder what the signal looks like. And actually up there looks like, in this case, 49 degrees has a much better end wave, up, slope, down, up, than the original one, which is more an impulse response, which goes up and then decays down. But once again, at 180 degrees, there's signal loss is just immense. Now here's our favorite gun, an AR-15, and it's actually a much cleaner signal than the 308. But again, you see here, since we're talking supersonic speeds for the bullet, you have the supersonic shockwave arriving, and then in this case, a half, 1.5, 2.5 milliseconds later, you see the muzzle blast, which is huge in comparison to that, arriving. But once again, as you increase the angle, there's a point at which the shockwave arrives at the same time as the muzzle, and remains that way for the remainder of the angles, and both the shockwave and the muzzle signal degrade down into nothing when you're directly behind the gun. Okay, so I've shown you the theory now, and this is from one of the leading experts in the field, and he goes into a lot of different some other guns, most of them just pistols, none of them having, although this is a 22 rifle. It's interesting, it almost looks like it has a shockwave here, but I don't think that's true. I think this just gas is escaping from the barrel that create this high frequency resonant there. Alright, so let's go talk about two real examples from the Vegas shooting. In this case, the first one I'm going to show you is over here in the parking lot of the Luxor Hotel, and it captures volley 9, and it's the Vostovich where they're speaking. I think it's Israeli or Hebrew or whatever, and so this is the recording. Let's just play a little bit of it. Okay, so you can hear it's a fairly clean signal. There's not a lot of background noise to cloud it or anything. Anyway, the next one will, anyway, this one is a fairly clean signal. You're going to be up a while?
No, I'm alright.
So, let's take a look at that in my favorite tool, the sonic visualizer, to see what this looks like. Now remember, we're looking at the supersonic crack first and the muzzle wave second. We saw the waveform, but let's look and see what it looks like. In this case, we're going to take a look at a portion of volley 9. And what we see on the top one is the power plot. On the middle pane here, we got the frequency plot. And on the bottom, we have this waveform. So let's take a look at the waveform, since you already know what you're looking for. So you'll see immediately that there are two signals, the one in front and then something later following it. And as we would expect, the first one is the supersonic shock from the bullet, and the second one is the muzzle blast. And here you can see that the muzzle blast is much wider in frequency, i.e. these little waves in here are wider compared to the supersonic crack. And because of that, the supersonic crack has a higher frequency than the muzzle wave. For us, in this example, we can measure the distance between those two, and it measures out to be about 54 milliseconds. Now, Mr. Maher was recording at 10, 20, and 30 feet, so his were very short in distance, and that's why they were 2 or 3 milliseconds. But the Luxor parking lot is, I'd have to pull up the map and measure it, but probably on the order of 450 feet or something, so we have a much larger lag. But you can see in this case that it follows the model pretty well. But what you also can see is that each one of these, I expanded it out there, does not look exactly like the predicted waveform, and this is due to the limited bandwidth of the recording and the environment. So that's a close-up view of what the shock wave looks like. Let's go over here and get a close-up view of what the muzzle wave looks like. Muzzle blast. And you can see it's a much wider signal. Now this happens to be a very pristine recording. Now, as you can see, there are multiple bullets here. There are multiple supersonic cracks. This is, let me get a drawing tool over here. This is one. This is a supersonic crack. That's a supersonic crack. That's a supersonic crack. And then this is a muzzle blast. Oops, I marked that wrong. This is a muzzle blast. That's not a supersonic crack. Hey, I wasn't paying attention. I was thinking about other things. Alright, so we got 2 of each, and that's perfect. And then over here comes another supersonic crack. They're not evenly spaced, so. But you'll notice that these are at different frequencies. If I wanted to measure that, I'd pull up my frequency tool here. He says easily. Alright. Let's see. What's this one? And so in this case, the peak of those supersonic cracks looks to be somewhere around 2 kilohertz. If I were to run the amplification up, we'll probably see more at the top. No, not much. And the bottom end of the supersonic cracks around 316, which overlaps with the top end frequency for the muzzle of 1400 and a low end for the muzzle of somewhere around 160. But they're still quite distinguishable, particularly when they're separated out by the lag. And if we were to shrink them up, and you could see how overall they tend to start looking like they're at the same time. And in this case, the red lines down here is I've marked the muzzle so I can export that into a program and look at it. And these signals up on top on the power supply here are actually echoes. And if you look close, you can see that they're echoes of this right. Let me circle it with my tool. This would be an echo of a supersonic crack, and that would be an echo of a muzzle. Okay. So that's for this location. Let's go right across the street to this location. Now, this is one of the early release body cams from the officers right there behind the rock wall on the boulevard. And as you can see, it records, a couple of single shots followed by volleys 5. There must be a mistake here because 6th and 7th are reversed, so it goes 5, 6, 7 all the way up to 8. So anyway, it's right across the street. Now, if the bullets were being fired this way, then as you can see, the angle for these two things, that angle for the Luxor is substantially larger than the angle for that, and therefore, based upon what Maher is showing us, is that the recording for the LVMPD would have a larger lag and a larger signal. So let's go ahead and take a look at the signal from that location. I've loaded it up already into Sonic Visualizer just to save some time. Now in this case we're looking at part of volley 5, which was that 3-burst volley, and it looks substantially different both on the spectrograms and where's my, must be over here. So I was trying to get a, there we go, a waveform plot. So first off, let's take a look at the waveform plot. Oh, we've got to identify the signals first before we go any further, because it's strange here. So we would expect the lag to be bigger, right? Right. So this, because it has a high frequency component, that's a supersonic crack. Now this is a supersonic crack. Oh, whoa, 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 you said. Wait a minute, now what happened to the muzzle blast? Well, it's got a big lag. That is, it's delayed quite a bit. The first muzzle blast we see is this one. Okay, so from this supersonic crack to this muzzle is the lag. So you see you get 1, 2 supersonic crack bullets before you get the first muzzle. So indeed, in that location, then let's go ahead and measure that. The lag is bigger. It is approximately 387 milliseconds versus, what was it, 50? I said 50 some for the other one. Well, let's just go back over there. It was measured as RON 3 measuring tool and about 66 in that particular instance. So you see it's 5 times larger just by going across the street. So as you can see, when the angle decreases, the lag increases. What about the signal strength? Is it, as Mr. Maher says, better? You tell me. It looks like a lot stronger to me. The width and duration, the width and brightness of these things kind of tells me that, but you know, those could be changed by this. But if you look at the relative ratio of the signals, then you'll see that the, well, let's just go over here a bit. Yeah, the supersonic crack is much louder than these muzzle blasts, which is, if we go back to the other one over here, then they're about equal, with maybe the muzzle blast being big, maybe being more prominent, just by a little bit. So as the angle increases, you know, well, there's a lot of dynamics going on there, and I'd have to sit down and actually calculate it. But this signal relative from the supersonic crack to the muzzle looks more evenly distributed than this one, where you have a very dominant supersonic crack followed by a much weaker muzzle. Okay, why? Because we're closer to the bullet. The bullet's flying, you know, at that lag, it's flying fairly close to us compared to the distance the shooter is away from us, which determines the intensity of the muzzle wave. And so here you can see overall, let's eliminate all the drawing on it. Eliminate that and shrink it down. For this volley, which has the first muzzle blast right there, there's 1, 2, 3, 4, 5, 6, 7 bullets fired. But on the tail end of this, you hear, I don't know if you could separate that, 1, 2, 3, 4, up to 5 muzzles that are after after the last sonic crack is heard. So you see the gap between them has increased substantially. And that's what, you know, comes into play when you're looking at this stuff. is this variation just by walking a couple hundred feet in the timing of arrival of the supersonic crack and the muzzle blasts. Very much different. Signals very much different. And while these weren't exactly the same volley, if that Luxor parking lot had recorded volley 5, we would have seen something very, very similar. Alright. So, what we just covered was how the signal of the sound signals from gunshots varies as you go off axis from the traveling path of the bullet, which is determined, of course, by the barrel of the gun. So, and in many ways this helps explain why the intensity of these sounds varies so dramatically, because that's exactly what Mr. Maher has measured and demonstrated to us. Is these are not uniform signals, but they are quite directional, based upon the angle between the bullet, or the direction the muzzle is pointing, and your location or the recording location. And you could swap that around. If you have a fixed recording location and the gun is weaving to and fro, then that too is going to have the same impact. All right, I think that's enough for this evening. So we'll grab you in the next one.